Okay, this week in lab we are doing an extraction experiment. So let's talk a little bit about the theory of extraction. Extraction is a general term for the recovery of a substance from a mixture by bringing it in contact with a solvent that preferentially dissolves the desired material. Now, our initial mixture can be a solid or a liquid. So therefore we have two types of extraction. We can have a liquid-liquid extraction where our original mixture was a liquid and then we are extracting with a liquid or solvent. Or we can have a solid. Our initial mixture could be a solid, and so therefore we'd have a solid liquid extraction. Again, this is our solvent, so our initial mixture was a solid. So there's two types of extractions that we can have: liquid-liquid and solid-liquid. This week we are doing a liquid-liquid extraction. Now, extraction is an important step for most organic reactions. Also in the isolation of natural products. You're trying to isolate some compound from some plant. We will use a solvent to extract our desired compound from the plant. We also use it in the lab when we do a reaction, an organic reaction. So it's one of the ways to purify compounds, to isolate those and to purify them. Now, our liquid-liquid extraction that we're doing this week, this involves the distribution of a solute between two immiscible solvents. Now, it's important that our solvents are immiscible. They must be immiscible. That means they do not mix. So we're going to have two layers in our reaction tube. Now you need to know which layer is which. So let me draw a reaction tube. So we should have two layers here. And the more dense layer will be on the bottom. So you need to be able to identify which layer is which. Which layer is our organic layer and which layer is the water layer. Well, it depends upon the organic solvent that we're using. It depends on the density of it. Some of the organic solvents are more dense and they will be on the bottom. For example, dichloromethane. Dichloromethane is often abbreviated DCM. And this week we are using dichloromethane as our solvent. Dichloromethane will be on the bottom. Dichloromethane has a density of 1.32 grams per milliliter. Water would be on the top, our water layer. Water, of course, has a density of 1. So this week in lab, the organic layer is going to be on the bottom. That's our dichloromethane layer. In some of the labs in the future, though, the organic layer will be on top. Most organic solvents are less dense than water. So let me give you an example of that. Diethyl ether is a common solvent. That's a very common solvent. We'll learn what the structure is here coming up in the future. But that's a very common solvent for a lot of organic reactions. And it has a density of 0.706 grams per milliliter. So you can see it's less dense than the water. Water, of course, we already said was 1. And so the organic layer is on top. So sometimes the organic layer is on top, sometimes it's on the bottom. Just depends on what our solvents are. So it's wise when we're doing extractions and trying to separate the layers, never throw anything away until we're certain, until we've isolated our compound and we know it's worked. Don't throw things away. You throw something away, it could be the wrong layer, and then your experiment's ruined. So we've got the two. This week in lab, we're using water and dichloromethane this week. So we've got the two layers. So we're looking at the distribution of our compound. We're using benzoic acid this week. And we haven't learned how to name compounds yet, but I'm going to go ahead and just draw the compound here. This is what benzoic acid looks like. So that's our molecule. We'll learn how to name things as we go along in lecture. By the way, the solvent dichloromethane, I'll show you that as well. This is dichloromethane. There's 2 chlorine atoms on a carbon. Okay, so we're looking for the distribution of the benzoic acid between the water and the dichloromethane. Now, benzoic acid prefers to dissolve in the dichloromethane, but it does, some of it will be in the water layer, but the majority of it will be in the dichloromethane layer. So we're going to calculate a distribution coefficient. What is the preference of it for the organic layer, for the dichloromethane? So let's look at a formula. So we're going to be calculating a distribution coefficient, or it's also called partition coefficient. And the symbol that's used is a KD, capital K with a subscript D. Now the distribution coefficient is equal to the concentration of our compound, whatever it happens to be. I'm just going to say compound C. Of course, it's benzoic acid this week, but I don't have enough room there. I'm just going to say compound C. In the organic layer, organic will be on the top here in our calculation. So in our organic solvent, and concentration is typically given in grams per 100 milliliters. On the bottom, this is going to be the concentration of C in water. And again, that would be concentration is typically grams per 100 milliliters. Now, we're going to be using different amounts of solvent this week rather than the 100 milliliters. So let's rewrite this. We're going to look at grams of C in organic solvent divided by the milliliters of organic solvent. Again, our organic solvent this week is dichloromethane. And this is all over grams of C in the water layer divided by the milliliters of water. Okay, so that's our equation for the calculation of the distribution coefficient this week. Let's look at an example. Let's say we have some compound, I'll call it compound B, and let's say the solubility in water, there's 2 grams and 100 milliliters of water. And the solubility in organic layer, let's say, again, we're using dichloromethane, but I also mentioned diethyl ether is a good solvent. I'll say in the ether. Solubility in the ether, 10 grams will dissolve in 100 mils. So our distribution coefficient, Kd, or partition coefficient, we'll have the organic layer on top in our calculation, always. And the water layer is always on the bottom here in our calculation. So if you do the math, we have a distribution coefficient of 5. Notice that that is unitless. Our units cancel out. So the distribution coefficient does not have any units. Now, what does that 5 mean? A distribution coefficient of 5. That means that our compound, whatever it was, compound B, is 5 times more soluble in the diethyl ether than it is in water. That's what our distribution coefficient is representing. How much more soluble is it in one solvent than it is the other? If we get a value of less than 1, then that would mean it would be more soluble in the water. But anything greater than 1, our compound is more soluble in the organic solvent. Now, when we do extractions, we're only going to do one extraction this week. But in the future, when we do liquid-liquid extractions, it is better to do several small extractions than it is to do one big extraction. Again, we're only going to do one this week because all we're trying to do is determine the distribution coefficient. But if we were trying to isolate as much compound as possible out of the mixture, we would want to do multiple extractions. It's much better to do several small ones than it is to do one large one. Now, I'm going to go through some calculations to prove that to you. And this will also help you with post-lab questions. So let me just write what I said there. It is better to do several small extractions rather than one large extraction. So let me prove that to you. Let's look at some calculations. Let's suppose we have 1 gram of compound B. I'm going to stick with my B that I had there a moment ago. In 100 milliliters of water. And let's say we are going to extract 100 milliliters of ether, the diethyl ether. I'm just going to abbreviate it ether for short. Let's see how much we would extract with the ether. So we're starting off with 1 gram in 100 milliliters of water, and we are going to extract with 100 milliliters of ether. So we already know the distribution coefficient. We just calculated it. The distribution coefficient was 5. And we know what the distribution coefficient, what the equation there is. It's the concentration in the organic layer divided by the concentration in the water layer. So we have X amount in the organic layer of compound B. I don't know how much went in there. That's what we're trying to calculate. We have 100 milliliters of ether. Now we started with 1 gram in the water layer, 1 gram of compound B in the water. But when we added the ether, X amount went into the ether layer. So I've got 1 minus X. We lost X amount. Don't know yet how much that is. We're calculating that. Now, we extracted, this was in the water layer, so 1 gram in 100 milliliters of water. Now, if you go through and solve for X, we'll see how much got extracted with the 100 milliliters of ether. And if you do the math here, we get 0.833 grams in the ether layer, the organic layer. So that's the amount that extracted, the ether extracted. We started with a gram and it extracted out 0.833 grams. So the rest of it would be in the water layer. If you can do the math, you can subtract it there. We'd have 1.67 grams in the water layer, still left in the water. So that was with 1 large extraction. Let's do it with several small extractions. Let's do 4 extractions with ether of 25 milliliters of each. That's still the same amount, but rather than doing the 1 large one with 100 milliliters, let's do 4 separate extractions of 25 milliliters each, and let's see how much we get. I'm going to write my number over here so we don't forget. So this was the large extraction. Was 0.833 grams. Okay, I'm just going to stick that over here. So, again, I've mentioned that it's better to do several small ones. So let's look at 4. If we do 4 small extractions of 25 mils each. Okay, our first extraction. Let's look at the first one. Distribution coefficient 5. So it's the same equation there we did there before. We're extracting out X amount with remember the top is the organic. So it's 25 mils of the ether. On the bottom is the water here. So we started with 1 gram. We extracted out X amount. And we had 100 milliliters of the water. 25 mils of ether, but 100 of the water. So if you go through and solve for X, you'll come up with 0.556 grams in the ether. And of course the rest of it would be in the water layer, so there would be 0.444 grams in the water layer. Okay, so that's our first extraction. Let's do the second extraction. We're going to do this 4 times. Distribution coefficient 5. We are extracting out X amount with 25 milliliters of ether. Now here is where it's different. Before we started with 1 gram of compound B and we extracted out X amount. This was in the water. There was 1 gram in the water layer. There's no longer 1 gram. We've already taken out 0.556. There's only 0.444 grams of compound B in the water layer. So that's what we're using here. 0.444 grams minus X. And this is still in 100 milliliters of water. Now, if we go through and solve for X, our second extraction takes out another 0.247 grams of compound B that is in the ether layer. The rest of it would be in the water layer. So if you subtract 0.247 from the 0.444, you get that there's 0.197 still in the water layer. Now, if you go through the same thing, I've got 2 of them there. I'm not going to go through the other 2. I'll just write the numbers up. If you do a third extraction, you'll come out and solve for X, you'll come out with 0.109 grams in the ether layer. Now don't forget, this was our water. You'll have to put that in there in the bottom now. Not the 0.44, you'll put the 0.197 when you do this calculation. So we come up with 0.109 grams in the ether. And the rest of it would be in the water layer. If you go through and do the fourth extraction and solve for X, you should come out with 0.049 grams in the ether. Okay, so there's the 4 extractions. How much was removed with the ether with 4 extractions. Now let's total these up. So this is our ether. Let's total all of these up. All 4 of those and see what we get. If you total those up, 4 small extractions of 25 mils each. We've extracted 0.961 grams. Now, remember our number from before, the 1 large extraction, we had 0.833 grams from 1 large extraction of 100 milliliters. You do 4 small ones of 25 each, and we've got out 0.961. So you can see it is better. We extracted more by doing several small extractions rather than 1 large extraction. Okay, so I went through all of that. That will help you with the post-lab questions that we have at the end of the procedure. Let's take a look at our procedure for this week. It says you're going to place 100 milligrams of benzoic acid in a reaction tube, and you're going to add 1.6 milliliters of dichloromethane. It's also called methylene chloride. So it goes by a couple of different names. And you're going to add 1.6 milliliters of water. And you should use the deionized water. There's deionized water by the sinks. They're in some squirt bottles. It says deionized on there. You always, anytime we're going to use water in one of our reactions or experiments, always use deionized water or purified water. Now, make certain you know which layer is which. The dichloromethane layer should be on the bottom and the water layer should be on top. So just make certain you can see that as you mix those together. You're going to put a septum on the top and shake your tube vigorously for about 2 minutes. Now, the septum is the little white rubber thing that's in your kit. I should have brought one in here to demonstrate, but I didn't. Try to draw it here. Okay, so the septum is white. They're in your kit, they're white. You've got a small end and a big end here. Put the small end down in the reaction tube. And then you're going to take the edge of this with your fingers and pull it over and hold it. You take your other fingers here on the other side. This stretches, this is rubber, this stretches, and you can flip it over on the other side. So it makes a good seal around this. So when you're done, put this in a different color here. So when you're finished, this is sealed around that glass. It makes a good seal so that it won't pop off. Then you can take and shake it up. Okay, so shake for 2 minutes. Set your reaction tube in your test tube rack and give it some time for the layers to separate. Give it another couple minutes for the layers to separate. And then you're going to take a Pasteur pipette and pull off the lower organic layer. Now, I don't know whether you've used a Pasteur pipette or not. They are disposable, and you have the little bulbs in your kit for those. So we have our two layers, should have separated. We have the dichloromethane layer and our water layer here on top. And you're going to take a Pasteur pipette, put the bulb on the top, and you'll take that pipette all the way to the bottom to get that bottom layer. Bulb here on top. Again, those is not a very good bulb, but you know what I'm saying. Squeeze the bulb and then it will slowly release it and it will suck up the bottom. You'll have to play with this. It takes some getting used to slowly release the bulb, and you're trying to suck up just the dichloromethane layer, our organic layer. You don't want the water layer. And so if you do that, suck it all up, the dichloromethane layer, leave the water layer in there. We'll transfer that to another reaction tube, I assume. Yeah, transfer it to another reaction tube, and then we'll dry it. Now, if you happen to suck up some of the water, again, it takes some getting used to. If you happen to suck up some of the water, just squirt everything back in the reaction tube, let the layers separate again, and try it again. You may have to try it several times here in the beginning. You'll get used to it after a while. You'll get good at it. once you get used to using these pasteur pipettes. But if you accidentally suck up some of the water, just like I said, squirt everything back in and allow the layers to separate and try it again. Okay, so you're going to put that into another reaction tube, the organic layer. We need to dry that organic layer. You're going to dry that with anhydrous calcium chloride pellets. That's our drying agent. And you want to add enough pellets to dry it. Now, how do you know when it's dry? There should be a few of the pellets that will move when you flick the tube. So when you put those in there, it will soak up the water, and those pellets will stick together, and they will not come apart. They grab that water and hang on to it, so they're clumped together. Now, if there's no more water in there, then, so maybe, I don't know, maybe 4 or 5 pellets clumped together. If there's no more water in there, then there's nothing for it to stick to. Then there should be 1 or 2 pellets that can move around. So if you had, say, 7 pellets in there and 5 of them clumped, then the other 2 should be able to move when you flick the tube. Now when you flick a tube, I'm going to use the marker here as my tube. You want to hold it at the top and hold it good and tight. And you want to take your fingernails and just flick off to the side. Don't sit there and flick like this. This does nothing. That will do absolutely nothing. You want to just glance off to the side. And if you do that and just keep flicking, you can go really, really fast. Everything should start spinning inside if you're good at it. So just flick off to the side, just glance your fingernails off to the side, and that will get everything spinning inside. You sit there and do this, nothing happens. So just glance off to the side with your fingernails is the best way to do it. That's flicking the tube. So it takes some time to dry. This is not instant. Give it at least 5 minutes to fully dry before you proceed. Give it at least 5 minutes of drying time. You wash your clothes and put them in the dryer. They're not dry in 2 seconds, are they? Take some time. Same thing here in the lab. Take some time to dry. So give it some time. Now, once it's dried, once it's had 5 minutes to dry, you're going to take and pre-weigh a 10 milliliter Erlenmeyer flask that's in your kit. So go weigh it, empty, write that weight down in your notebook, and then you're going to transfer the organic layer that's on our pellets. You'll transfer the liquid over into the Erlenmeyer flask. So we have, you can use a pasteur pipette. So you've got your reaction tube, we have the dichloromethane, you have the little pellets, calcium chloride pellets there in the bottom. And so again, we're going to use a pasteur pipette. Those pellets are big enough, they're not going to get sucked up. You don't have to worry about it. So take your pipette all the way to the bottom and suck up the dichloromethane liquid along with the benzoic acid. It's dissolved in it, and leave the pellets behind. So you'll transfer that over into your pre-weighed Erlenmeyer flask. You're going to rinse the calcium chloride pellets. There could be, so we've got all the dichloromethane. Looks like we got all of it sucked up, but there still could be some still on the pellets. So you're going to rinse those. It says with 2 small volumes of dichloromethane. So go get some fresh new dichloromethane. Just says a small amount, doesn't say how much. I don't know, maybe 0.1 mils or 0.2 mils, something like that. Put in there, you're going to wash it, suck that up, put that in your Erlenmeyer flask. Said do it twice, put another 0.1 or 0.2 mils in there. You don't have to measure it out, just said wash them a little bit. We're just trying to make certain we get everything off our pellets and into the Erlenmeyer flask. So a little bit more, suck that up, and get that into the Erlenmeyer flask. So that way we've got everything loaded into the Erlenmeyer flask. You're going to put a boiling stick in the Erlenmeyer flask, and then we're going to heat this on a sand bath. So take the Erlenmeyer flask, just set it on the sand bath. The sand bath has a variac, that's the controller that controls the temperature, and put the variac on a setting of about somewhere between 1 and 2. We don't need a very high setting. Dichloromethane has a very low boiling point, so a setting somewhere between 1 and 2 should be sufficient. And we'll evaporate all of the dichloromethane off. The benzoic acid that it extracted should be left behind, so you should have a solid left in your Erlenmeyer flask when we're finished. You'll take and weigh the flask. Once all the solvent's gone, no more liquid, just white, solid benzoic acid left behind in the flask. Take and weigh the flask, take your boiling stick out, weigh the flask, and then subtract the weight that you had up here earlier of the empty flask. And that will give you the amount of benzoic acid that the dichloromethane extracted when you subtract the two. So that's the amount that's in the dichloromethane. You know how much you started with. You started with 100 milligrams, and let's say we extracted 90 milligrams, then the remaining 10 milligrams was in the water layer. So you can subtract however much you had there from the initial amount, and that's the amount that's still in the water. And so then you can plug your numbers into the equation there and calculate the distribution coefficient or partition coefficient, whichever you prefer to call it. Okay, so that is the theory behind this week's lab.